Good morning. Just for sound check, how is it right now? Do you hear me well? Sound check 1, 2, 3. Thank you, Zach. Great. Okay, let's start today's lecture with just the announcement. So the project groups already almost completed. I will share the recent position. It is the recent part. 4 groups already formed by your suggestion. 5 still missing 1, 2 person, and the rest didn't complete it yet. So if you didn't send me the names, you can send me still for today, and otherwise I will put them into the random groups with the random names. Okay, so this is the recent situation. So if you need to change anything, you can still change. There is no problem. So this is the recent case what you send me. Another point, so the important days for the project. The first week, introduction of the project ideas and formation of teams. The second week, that is the week we are in right now, the project proposal. It is at least 1 page written document showing the specific objectives of the projects and the subject. So identify the machine to be assembled or disassembled. Justify the significance of and group motivation for the project. Identify the intent method. What kind of tools are needed? The computer tools, some SolidWorks or some drawing programs, such kind of thing. And suggest a timeline for completing the work. So timeline already given as a tentative in your syllabus. That is the one you are going to adopt this one to your case, and suggest duties of the group members. So I expect this is going to be done this Friday. Okay, so until this Friday, you are going to come to me with some suggestion, and that is not going to be 100% the absolute one. So that is a just suggestion, and I will give you some uh, uh, advice, and you might need to do some more or change the topic, whatever it is. So that is going to be a kind of check in terms of the topic and in terms of the content. So this Friday, I expect you will come up with the first draft proposal. So in terms of the project, you're supposed to come with your first draft project proposal, of course. If you have any question, please write onto the chat board, or you can raise your hand. Okay. So this is the last situation of the groups. And another announcement, I have already posted the homework. So the homework 1 posted on the Blackboard. Those are the same questions, similar questions with the end chapter problem 114, 26, 382, and 469. This is a kind of review from the earlier fundamental class, and there is going to be a quiz accompanying this one. This is going to be 80% of the assignment, and quiz going to be 20% of that assignment. So that is the combination going to be 80% and 20%, the entire grade for your first assignment. And the quiz one not posted yet. The reason it is going to be uh, probably very small, let's say 20 multiple choice question, and for very short time. So as soon as you access the quiz, you have to finish at once. But first of all, you have to complete your homework. There are some questions from your homework, so I would like to be sure you yourself already completed by your work. So I have some question from the quiz problem, the homework problems. So those are referring you, just I would like to understand you did your homework or you copied from somewhere else. So that is going to be a double check for a kind of check for this. Okay. Now, if you are not using the sound, please turn it off. Okay. And we are going to start here right now. That is, last time we started with reviewing chapter 1, and we talk about what is design and design process and design consideration. We talk about computational tools, acquiring technical information, and we mentioned some useful internet sites and some organizations. Those are especially for the standards and codes, so those are important ones when we are going to talk about the components itself. For example, bearing, the gears, those are already have some codes and standards, and those codes and standards determined by some of the associations. So the name, some of the names are listed here. Those are the most important part. If you're interested in one of them, just go and try to get in membership. So the membership is very easy for the students. They are encouraging the students for membership, and they are providing too many materials with some very symbolic fees. And I encourage you, especially you should get a membership, American Society of Mechanical Engineers, ASME, if you are not yet, and American Society of Testing and Materials. These are important two associations. Other than that, the others a little bit the branches or some specific associations. So if you are interested in steel construction, that is, if you are interested in gear manufacturers, those are already listed here. So those are a good list. So tolerances, we talk a little bit, but that is important part in the design. When you are designing anything, that the cost, one of the important parameter, and we generally do, we consider three main part in our analysis for the design. The first one is material. The second one, stress, strain, or deflection analysis. And the third one is cost. So if any of the structure or any of the design is not feasible, then it will be not good. And the one of the important the consideration and the cost, that is tolerances. So the tolerance change when you look at the, let me make it bigger. Okay, tolerance change with the excuse me, cost change with the tolerances. And what we see here, this is the area, and in that particular level, let's say we use only rough turn, semi-finished turn, or finished turn. Those are the kind of the machining. So if we are not going beyond that one, then that is rough, very rough machining operations, and the cost is small, cost is low. But if you go with the grinding and then next honing, then the cost increases drastically. The reason, actually, you have to put too much expense, the money to make this machining processes. For example, a cylinder, the engine cylinder, internal combustion chamber cylinders, those need grinding and honing, and that's why they are expensive. But if you are using any component, the surface finish is not really important, like we said in the in a cylinder, in an engine cylinder. Then we don't need to make perfect finishing on that part, and therefore we generally see the most of the machine components having or machined in that low level operations. And they require additional processing step, require additional inspection, require machines with lower production rates. So the close tolerances generally increase the cost. That is one of the important rule. And another rule, break-even points. In the manufacturing, we need to know how many part we are going to produce or we need. If the number of parts is not very high, then we don't need an automated processing. The manual processing is enough. So in this graph, what we see, the cost and the production, and in this, could you turn off the mics or the okay? Okay, thank you. That is the cost between cost and production changes, and this is an example for a screw machine process until 50 parts. It is break-even points. So until this 50 parts, the hand screw is better. But if you are if you need more than 50 pieces, then automated going to be better. So always there is a break even point in the production, depend on the number of the pieces. So that is another important issue in terms of the cost of that that component. And safety and product liability. This is another issue in design. So strict liability concept generally prevails in the United States. It is very important, and it is maintained by some regulations. This is very, very important. Manufacturer is liable for damage or harm that result because of the defect. So you need to maintain, you need to provide the maximum liability for what you are actually the producing. Negligence need not to be proved. Calls for good engineering and analysis and design, quality control, and comprehensive testing. That means we need engineering. We always need engineering for any product. So it is not uh, correct to make any of the design with trial and error. We need the earlier work on that design and make some analysis, some material analysis, some stress strain, deflection analysis, and the cost analysis. But in terms of the safety and product liability, we definitely need some stress and strain analysis to be sure it is liable. And this is very important. Another two terms: strength and stress. So sometimes we confuse these two parameter, these two term, this two term comes up. We intensively use these two terms. The what is strength? Strength an inherent property of material or a mechanical element. That means every material, for example, if it is a steel or if it is an aluminum, and of course the type of steel, type of the aluminum, every material has its own strength. So that is sometimes depend on treatment and processing. What is the way we are manufacturing this material? Those are all affecting the strength of the material. So may or may not be uniform throughout the part, but generally in our analysis, we assume it is perfectly done. So in many of the analysis, we say this is isotropic. It is an homogeneous material. That means the uniformly distributed, that all the property are same in all the direction. So that is a kind of assumption. But of course, in actual, in real world, in real world, nothing is perfect. Every material has some uh, uh, flaws and discontinuities, some manufacturing errors. How we are dealing with this one? So the next step going to be design factor. So design factor or safety factor generally compensate this problem. So the ultimate tensile strength, yield strength, those are some property that is belonging to the specifically the material. Might be steel, any of the steel. For example, you are using, yes, stainless steel. So the stainless steel has its own ultimate tensile strength and yield strength. And stress, this stress is a term we are using, a state property at a specific point within a body. So let's say you have a piece of bar, and that is a steel bar. So it has a strength let's say it is bearing to 100 megapascal tensile strength. So if you are applying like 50 megapascal, that means that is the stress you applied. But the strength of the material is 100. So therefore, the stress is a state property at a specific point within a body. So primarily a function of load and geometry, sometimes also a function of temperature and processing. This is defining what is stress. So there is always uncertainty, as we said earlier. So one of them is deterministic method, and the another one is the statistical approach. But generally, we use the deterministic method because we don't have enough data about those situations. So the deterministic method establishes a design factor ND. What is ND design factor? That is loss of function parameter divided by maximum allowable parameter. So the loss of function parameter, maximum allowable parameter. So for example, the parameter is load, then maximum allowable load, loss of function load divided by ND. This is the design factor. And the safety factor, that is another, actually we are generally use it interchangeably. So the factor of safety is realized design factor of the final design, including rounding up to the standard size or available components. So this is, we use this factor of safety interchangeably with the design factor, but there is a little bit difference. The factor of safety is realized design factor of the final design. So we are considering every aspects of the things, the losing. So that is going to be final. And dimension and tolerances. There are some term in this part. We need those in our later sections. So those are important: nominal size, limits, tolerance, bilateral tolerance, unilateral tolerance. So we are going to use those. Please look at these terms again and remember. And the units. At the end of the first chapter, we have some different, actually two, the unit system we are going to use throughout the book, and one is SI system, and the second one is the custom system. So international system of units, that we call it SI. The base units are meter, kilogram, and second. So derived unit is Newton, and that is the base. Then the other parts derived, and the second one is the custom unit. So US customary foot pound system, and that is two standard gravitational system used by the engineering in this approach. And I believe you are familiar those things, and please remember those part as well. We are going to use both of them throughout the book. And the second chapter, it was talking about the material. And as I said, in design issue, in our analysis, the first part we are looking, or we are considering in terms of the material. So what should be the material point or the criteria we need to know. So in this part, we are learning what are the bases what are the basic terms, parameters relevant to the materials. So generally we start with a tensile specimen. So tensile test is one of the common tests we apply to any of the material. Might be polymeric material, might be metal, might be ceramic. So those are going to be the value or the data we collect with the tensile test, and we determine what is the ultimate tensile strength of material, what is the yield strength of the material, what is the toughness of material, the resilience of the material, or we can determine it is ductile material or it is a brittle material. So those information comes with the tensile test. And tensile test, we need to know what are the, just a second. So in a, we need to know what are the some of the terms important. So one, the stress. So stress defined as two actually way. One is engineering stress. So engineering stress means it is sigma, that is the symbol we use, and applied load divided by cross-sectional area. But we consider this is an initial cross-sectional area. We change the, for example, I apply 500 kilogram, and this is divided by AZ, that is, let's say, 10 uh, millimeter square square meter, or whatever the unit is. So it is 500, and if I change this one to 600, still, if I am keeping this 10 over there, no change. Actually, in actual test, that should change, because you are extending you are applying P onto the specimen, and you expect there is going to be some contraction on the cross-sectional area. But if you are not considering that one, always you are keeping this one as same, so the original cross-sectional area considered, we call it engineering stress. So that is engineering. If we consider that is not initial stress, it is like changing, let's say 9.8, so it is little bit little bit less than the initial cross-sectional area. Then I say this is something different than the engineering stress, and I call this one true stress. True stress. So true stress and engineering stress, those are different than each other. Generally, if you are in the first level, if you consider the stress strain curve, and if you are in the part of elastic region, so that is good to consider the original cross-sectional area. But if you are working in the plastic deformation side, it is considerably high, so you cannot ignore this momentarily cross-sectional area. So you have to always look at what is the cross-sectional area momentarily, the corresponding to the stress level. And what we need to know from a stress strain curve, this is a typical stress strain curve. So that is first proportional limit. That is the one actually we suppose there is no any change in the linear change take place until that point, and those the value, if you remove the load in that point, that the material will go to its original shape. And it is a kind of elastic limit, and the elastic limit defined just above, little bit above this plus proportional limit, but we are not considering these two are not very useful in terms of the practical application. Generally we consider y, that is the point we generally say yield point. And what is the meaning of the yield point? That is the deformation, the plastic deformation starting point. So until the yield point, we assume there is no plastic deformation. What is plastic deformation? The permanent deformation. So material, if we remove the load until that point, the material will go back to its original shape. So that is a kind of elastic deformation. But the plastic deformation means as long as you had some permanent deformation inside the material, or if you remove the load, it is not going back to its original dimensions, then you call that one as a plastic deformation. And why it happens, if you consider, if you remember your earlier material information, we talk about dislocations. So the first of all, when you apply extremely high stresses, loading onto the material, uh, uh, if you are not having any motion on the dislocations, so there is no any permanent deformation. Those are all elastic, those are temporarily. But as soon as you had some the motion dislocations, the motions of dislocations, then it is permanent. That means you change something inside the material and it is not reversible. It is not reversible. So this yield point generally considered as the border before and after the permanent and temporary deformation take place. So before, we call it elastic region, that is the uh, temporarily change happens, and beyond that point, if you exit that yield point, that means you have some permanent deformation on the material. And we are determining or defining this as a yield strength. So yield strength, one of the important parameters we are going to use throughout the uh, book, and that is meaning if you are under that point, that means you are in safe zone. But if you exceed that point, that strength, that means you induce some plastic deformation. So yield strength defined at a point where significant plastic deformation begins or where permanent set reaches a fixed amount. So generally it is considered at 0.2% of the original gauge length. So as we see here, if you have this curve, you can very easily say this is the yield point. But in some cases, you cannot see exactly what is the turning point, the knee point. Then you need to define the yield strength. So generally we use 0.2%. So if you put this 0.2% here and draw a line parallel to this change, So it eventually it will cross, it will intersect the curve. So this point defined as the yield point, and the maximum point we obtain, we record, that is called ultimate tensile strength point. So here it is the ultimate tensile, and that is the one for the for this curve, ultimate tensile. Actually, this point is having much more higher loading, but as we define the engineering stress and true stress, so if you consider always the original cross-sectional area, it is going to be something like this one. But if we are going to consider what is the momentarily cross-sectional area, then that is going to be the true stress and engineering stress. This is for original, this is for momentarily cross-sectional area. And the equations here, what we use, sigma equal P A0, that is cross-sectional area, this is applied load. If it is round specimen, then 1/4 pi d square, that is the cross-sectional area. It is not necessarily be a round specimen, might be the different triangle or square or rectangle. So if you have rectangle specimen, then you need to again define what is the cross-sectional area for that one. So this is for good for only round specimen. And the strain defined as the length, the final length, this is subtracted, that is the original length. So this is a difference between before and after loading and divided by the original length. That is called strain. So therefore there is no unit for this one, because it is the distance or length divided by length. So the strain does not have unit, but this sigma, that is the P over A0. So this, if it is Newton divided by cross-sectional area, what was the cross-sectional area? That is millimeter square or meter square, and that is, we call it Pascal. So in of course in SI unit. And what we define here, that is the Hooke's law. So in the elastic region, not plastic region, it is not valid in the plastic region, it is valid only in the elastic region. The sigma equal E epsilon. Actually we define what is the curve over here. So in that stress, that is the P over A, and strain, that is epsilon. So what is the relation between these two guys? So that is stress equal epsilon. It is changing with a constant. So what is that constant? Actually it is the slope of this curve. Therefore we call it Young modulus or modulus of elasticity. So that is another important term, concept we are going to use throughout the book. And E is relatively constant for a given type of material, and we can pick up it from the catalogs or from different sources. Every steel has its own modulus of elasticity. Copper has. Generally, it doesn't change from the alloy to alloy. the steel, all the steel, if there is no change, considerable change in their chemical content, we assume the most of the steel has same modulus of elasticity. For example, considering 1010, 1020, 1040 steel, there is just a little bit change in the carbon content. It is in the 100% or 1000% rate. So that is not affecting the modulus of elasticity. But considering the another steel, it is another common steel that is, let's say, uh, stainless steel. So it has 12%, at least 12% chromium and some nickel. So it changed the chemical content considerably. Therefore, the modulus of elasticity will change. Uh, that's the same thing for copper and aluminum alloys. Another important issue here, we are going to use that part in our calculations, is the stress or strain hardening. Sometimes we call it work hardening. So if you are applying some let's say uh, if you are applying some stress and you are over the yield strength of the material, yield stress of the material, then imagine this one. So you are extending the specimen and you are exceeding the stress yield strength point, and then coming to one point that is not still the ultimate tensile strength of the material. In that point, you remove the load. When you remove the load, you have some permanent deformation, but the material goes back, it tries to goes back to its original uh, shape, but it cannot because there is some permanent deformation. So this is going to be plastic deformation, and that is the recovered elastic deformation. And if you try to have the same tensile test on the specimen, already had some tensile test, that is the one, actually not the same one with the original, because we induced some plastic deformation on this material. We created some permanent deformation on this material. So when we pull this material again, the yield point will not going to be same with the earlier one. So we call it cold work or strain hardened or hardening of the material. So any of the material, any of the steel, any of the copper, aluminum alloy have this uh, property if it is not already done before. So that is called cold work or strain hardened. I'm going to give you an example. If you want to break a small wire, what you do actually, uh, you are bending it back and forth. So with this back and forth uh, the bending, what you do, you are inducing, putting some uh, strain hardening onto the middle of or bending point of that wire. So what happens? It is gaining some stress. Actually, it is much better than higher than the original material. If you bend 3 times, 4 times, 10 times, so eventually it becomes very hard material, very strong material. However, it loses its ductility. So this is always, there are some very small exceptions. We can generalize it. Generally, if you increase the strength of material by cold work, the material becomes very brittle. So at the end, when you try to bend this one, it cannot bend because it is already had too much hardened, and it is very brittle like a glass, and it breaks. So it is also associated with the motion of dislocations, as we talk about the plastic deformation of material. In that part, we need to remember also what is the true stress and true strain. I partially uh, talk about that, and that is momentarily cross-sectional area considered. So true stress is based on actual area corresponding to current P. And true strain different than the engineering strain. So the length, that is the final length divided by original length. So that is already defined here as engineering strain L minus L0. That is the difference between the length before and after applied load divided by original, but this is called engineering strain, and that is called true strain. So that is ln, the logarithm, L, the length, the final length divided by original length, the initial length. And there are some relation between these two guys. So if you know what is the true stress of the material or true strain of the material, then you can easily get what is the engineering stress, engineering strain. So here, if you consider that is constant before and after the deformation, so that is going to be a kind of relation between the true stress and true strain. So here, if you know what is the strain, engineering strain, and engineering stress, so you can get what is the true stress. And if you know what is the strain, engineering strain, you can get what is the true strain. One another point here, torsional strength, it is very similar to strain stress or tensile stress graph curve, but here what we actually draw the twisting, what we say applying a torque here, trying to twist this material, and it is going to give very similar graph with the stress strain curve. At the beginning it is linear, then non-linear, so that is the part actually, but here that is tau, that is the shear stress, and here that is the strain, shear strain. So when you consider this shear stress and shear strain, then we'll have this equation, but in this equation we define G, that is the shear modulus or modulus of rigidity, instead of Young modulus or modulus of elasticity. So it is very similar, and that is another important parameter we are going to use later. Resilience and toughness. The resilience is the capacity of a material to absorb energy within an elastic range. And if you say what is the toughness, so toughness, the capacity of a material to absorb energy within its plastic range. So entire area gives the toughness, but only the elastic region gives the resilience. So I will stop here, and please sign in before you leave. It is already open, so self check-in is currently running. Please do it, and if you have any question, please write onto the chat board, or you can talk to me right after this class. I have office hours, so you can connect, and we can talk if you have any concern. Okay, thank you for your attendance today, and we see you on Wednesday. Bye now.